Okay, in this video, we're going to look at parabolas in a different way. In this video, we're going to talk about the focus and directrix of a parabola. The focus is this point here. It's a really special point within the parabola, within the bowl of the parabola. And the directrix is this line. It could be horizontal or it could be a vertical line depending on which direction the parabola is opening. But it's this line here that this parabola is from. Just know this, the focus is always the exact same distance from the vertex as the directrix. So whatever this length is, the length here is also the same thing. And it pretty much defines every point on the parabola. No matter where that point is, the distance to the focus and the distance to the directrix at that point is always equal to each other. For example, I chose a point here. The distance to the focus and the distance to the directrix is also the same. So all the points along this parabola are going to be equal distant from the focus as well as the directrix. They have an equal distance there. Now, why is all that important? Well, I will explain why it's important. All right, so take this picture. It's a picture of a satellite. And just so you know, a radio wave is a form of light. So you're going to learn at some point in physics that radio waves are basically a low frequency of light. So if you think about the light that you see, radio waves is not any different from it, other than it's at a frequency that we can't see, but we can hear. So anyway, just keep that in mind. So let's think about a satellite dish. It usually operates listening for something that's out of space. So let's say this radio is out of space. It's a satellite that's sending you your AT&T UVerse or DirecTV reception, whatever that case may be. All right, so that satellite dish is shaped this way for a reason. It basically took a parabola, some parabola, and they spun it around in a circle. And when they spun it around in a circle to create this bowl that you have called a radio wave, called a satellite dish, that's on the side of your house or maybe in your backyard or whatever else. Now, what it's listening for are radio waves. And if they just put this little receptor here in the ground, and it was listening for those radio waves, the radio waves would come and they would hit this receptor. But some would miss, maybe hit the side of the pole. Some would miss altogether, hitting the ground, and wouldn't give you a very good reception. It would get a lot of the light coming from that satellite, but it wouldn't get as much as you want because some of it would miss. So that is where the focus comes in at. So instead of putting the pole there on the ground, they actually chose to use the satellite dish. Everything here on this parabola, sound, light, whatever, if any of it struck the parabola, it automatically bounced back to the focus. No matter where it struck it at, it automatically bounced back to the focus, hence the word focus. So no matter where it touches this parabola, that sound, that light, whatever the case may be, whatever is reflecting from it, reflects back to the focus. So because this is made from parabola and it has a focus point, a focal point, now whenever you want to actually receive a radio signal from outer space, some are going to hit directly onto the focus point. However, some are going to hit the side of the bowls of that parabola, and when it does, it's going to bounce back to that focus point. So no matter where it is, it's going to bounce back to that focus point. So instead of just getting just the ones who originally struck the parabola, now you're getting everything. And depending on how big that bowl is, you're collecting a whole lot of light. It really amplifies how much of that light you can actually receive. So now instead of receiving just the stuff that struck the top where the focus point was, now you're receiving 100,000, maybe even possibly 1 million times as much of that light. Meaning you can see a lot further away. Hence, we actually can listen to television and use the internet and that sort of stuff using those radio frequencies. They're on the other side of the planet or even out of space, or we can listen to sounds that are on the other side of the galaxy. So anyway, this is the reason why it's useful, and that's how we use it, and that's the whole purpose of actually studying this focus thing. The Directrix didn't have much usefulness other than the fact that it's true that this length and that length are always the same, and we talk about it a lot, but the focus is really the really important thing that we use in technology every single day. So that's why we're studying it, and that's why it's useful, and that's why it's so important for us to actually figure out where it is in these parabolas. And what makes it so awesome is it actually works in reverse too. For example, if you just took a light bulb and you turn on the light bulb, the light will go in all directions, illuminating the entire room. However, if you put something around that light bulb, for example, a parabolic reflector, instead of it actually going all around the room, that light bulb is now a flashlight. So you actually open up a flashlight, you probably see a silver backing behind it. It's because whenever that light shines, now everything goes into one direction, which is directly outward. So instead of it being illuminating the whole room, it concentrates it. It tells it directly where you want that light to go. That can work also with sound. You can have some parabolic reflectors. If you go to certain museums, they may have a little whispering booth, a tunnel. You can sit right here, and you have a friend sitting on the other end. And as long as you talk to each other, it could be on the other side of the building, very far ways away. When you talk, your sound's going to bounce off this and go over there and bounce back to your friend. So no matter what you do, you can actually hear each other speaking from long distances. I know I've seen one at the Fern Bank, but it's a really popular thing to do to actually have those little whispering galleries or whispering tunnels where you sit there, your head's near the focus, and as you speak, your sound leaves your mouth, bounces off the walls of the parabola, and then bounces over to your friend's ears, and vice versa. And then you can see yourself standing out right here, like closer together, and you could be speaking and not actually hear each other, but here you could. So it's really neat stuff. It's really useful, and we use it a lot in math. So that's what we're going to talk about in this lesson. All right, so the standard equation for a parabola, not quadratic, but for a parabola, with the vertex at the origin is this. It could be this one, x squared equals 4py, or it could be that one, y squared equals 4px. We typically used to look at parabolas with x squared. They typically look like this. They open upwards, or they may open downwards. Parabolas with y being squared look different. They can open sideways. They're not functions because they don't pass the vertical line test, but it could be a parabola opening sideways that way, or it could open backwards this way. So in that case, that would be a y getting squared whenever it turns sideways like that. All the other rules pretty much apply just like it would be x squared, and you can find a parabola by plugging in different numbers for x. You can get different outputs for y, and you end up getting that curve. All right, so anyway, that's the standard form for it. Some other stuff you need to know is this. The focus for this type of parabola will be at the point 0, p. We could talk about how to find p in a minute. If the y came first, well, the focus would be at the point p, 0. All right, so if you actually want to find the focus, that's what it would be. The directrix would be at the line y equals to negative p for that one. And this one would be x equals to negative p, whereas this is a vertical line. And this is horizontal. It makes sense that be vertical because remember this one has a graph. It's turned sideways, so the directrix should be some vertical line. And the axis of symmetry for each of those are this. And the axis of symmetry for this one is x equals to 0, and this one axis of symmetry is y equals 0. So that would be a vertical axis of symmetry. That would be horizontal axis of symmetry. All right, so anyway, those are the facts you need to know about them. All these things go together. Everything on this line goes together. And I'll get that as a note because I'm about to erase the screen, add more information to it. All right, so this example says, identify the focus and the directrix of the parabola given by x equals negative 2/5 y squared. So you have to decide which of the formulas you're going to use, which standard form. The first one was x squared equals to 4py, and the second one was y squared equals to 4px. So we look at this equation, I got to decide which one of these should we be working with. And if you notice, this one has a y squared, this one doesn't have a y squared. So I must be using this equation. So I don't need that one. I'm using this equation. So I want to make it look like this. Y squared equals to 4px. So I can decide what p is. If I decide what p is, I can find the focus, I can find the directrix, because both of those are related to p. So this equation right now says x equals to negative 2/5 y squared. And I want to get it to say y squared equals, like that one says y squared equals. So to get that alone, I should divide this side by negative 2/5. So if I divide that by negative 2/5 and divide this by negative 2/5, you should wind up getting these cancel to be 1. So you wind up getting y squared equals to x divided by negative 2/5 should be negative 5 over 2x, because you got to multiply by the reciprocal. So given that, we now have it basically the same as this one. So what I want to do is, well, if this is in front of x, this 4p is in front of x. So 4p must equal to negative 5 over 2. So I can figure out what p is. 4p equals negative 5 over 2. I could solve it for p by dividing both sides by 4. And you divide that by 4, you should get p equals to negative 5 over 8. So I know p has to be negative 5 over 8. So if you remember, in this parabola, the focus should be at p0. Since I know what p is, negative 5 over 8, so the focus should be at negative 5 over 8, comma 0. And the directrix has to be x equals p, directrix. X equals to p. So since p is negative 5 over 8, x equals to negative 5 over 8. So we found a focus, we found a directrix, we've answered the question. Let's do a different one. All right, so the next example says graph the same equation we just looked at. So in order to graph it, the most surefire way of graphing any parabola is using a table of values. So typically we plug in numbers for x, but this one is solved for x. So you may be plugging in numbers for y. But generally I don't like doing that. I generally like to solve it for y. So I would solve it for y first. So I would actually divide both sides by negative 2/5, which we've already done before. And I would get 5 over 2, negative 5 over 2x equals a y squared. So the square root of negative 5 over 2x equals a y. Let's go call it positive or negative. So I can plug in numbers for x. I'm going to call it 1, 2, 3, 4. And if you notice, I plug in 1, I get the square root of 5 over 2 times 1, which is negative. So it's going to be plus or minus square root of negative 5 over 2, which is imaginary. So because of that, I don't really want to use numbers on that side of 0. I may want to use negative numbers. So instead of using positive 1, I should use negative 1, negative 2, negative 3, negative 4. So we'll take the square root of them. It's going to be the square root of negative 5 over 2 times negative 1, which gives you a positive square root of 5 over 2. So it's a real number I can find the value of. So let's do it that way. So when I square root this, I should get about positive or negative 1.58. And the square root of negative 2 should be positive or negative 2.24. Square root, when I plug in 3, I should get positive or negative 2.74. I plug in negative 4, I get positive or negative 16. We already knew the vertex at the origin, because all these we're looking at right now are vertex at the origin, because it defines the formula. The vertex had to be at the origin of it. So anyway, that's one point. Let's plot the other ones. Let me erase some of this stuff so it looks like it's going to be facing this direction. All right, I'll make my points green instead of red. So at negative 1, I get about 1.58, which is about here, or negative 1.58, which is about there. And negative 2 is about positive and negative 2.24, so it's roughly here and here. At negative 3, it's positive negative 2.74, so it's about there, roughly there. At negative 4, it's positive negative 3.16, so roughly here and here. So I see the curve. It's clearly that. And also, I knew my directrix, the p-value, is negative 5 over 8. Your focus was at 5 over 8 away from the center, so it's about here. And the directrix is this line, which is 5 over 8 behind. So this is my directrix. I should recognize this point as my focus. It doesn't actually connect with the center. It's kind of like right there in front of it. But anyway, that's all I have. Good luck.